Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
All right, hello everybody.
It's hard to talk to people electronically without a microphone.
Yeah, I was like, wait
that
a
was
minute.
smooth.
There's supposed to be a thing here.
There should be
Where
something
is
in front
it?
of my mouth. See, you should have taken mine because I was just going to start by saying thank you to anyone who was in Montreal at the Electrochemical Society meeting. And thank you for coming to the booth to talk to me because you took my voice away. And this isn't like a romantic gesture, like you took my breath away. No, like literally my voice has been, it's actually in my head. I don't know how it's coming out to all you fine people. In my head, it feels gone. I was struggling at the booth for many of the days. Like after the first night, first night, it's like there's a poster session and reception, and the exhibit opens for a couple hours, and then I woke up the next morning, like the first full day of the conference for us anyway, for exhibitors, and I woke up and I was like, it was like, oh no, I have to talk for my job today, but I'm not sure I can do it. So it was fun. It was good. But
you sound fine.
I
sound
feel
great.
I feel like when I get going, it's all right. But like when I, it's like when you wake up after what you haven't talked, you're sleeping. Sometimes you're just like you're working out the kinks of waking up. Sometimes there's like the voice needs to get warmed up. I feel like one of those don't singers or like opera singers, they do like the me my mom, they like warm up their voice before la 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 la, yeah, that kind of thing. Well, there's no equivalent for talking about electrochemistry on a podcast. They just go like,
impedance spectroscopy.
The Human Torch was denied a bank loan. Unique New York. Name that movie reference if you can. Welcome everybody. I will do my best to speak for another 2 hours with a voice that exists, and then later I will have no voice again, probably, because all I do is talk. And that's a me problem. But thank you for joining us. You can see up here, again, 100 episodes. That was last week, but we're leaving it here because I like it. It's fun. It's festive. There's balloons. You can't take that away from me.
Yeah, we're still in celebratory mode.
It's true.
It's not just like, oh, it's like 100 episodes this last week. Well, we can.
That's right.
We're still remembering
it.
Not everybody attended last week, so we want to keep letting you know.
We should have put 101 episodes, but that's not as festive.
That's not as festive, unless I put white and black dots, and then it's like, oh, now it's Dalmatians theme.
Oh, that would be cool. 100. Oh man, that would have missed opportunity. Oh god. All right, we got to start this whole thing over and get to that.
I don't want Disney to sue me.
No, that's true. Yeah, they do that. If anybody has like a Dalmatian at their house, Disney writes like a cease and desist order. Like, you can't have that dog. That's ours. It's just my pet. I don't know.
My dog.
Okay. Well, let's get right into it, I guess, then. So Tiki has a few questions to start. Let me see here. So Tiki says, if we want to test a battery, we need to mimic the real system. For example, our mobile, a load. Okay, like a mobile phone. I guess.
Yeah. So the phone is the load. I guess.
That's fair. Okay.
Okay. Right,
so we only talk about voltage and current, and never about the resistance or load. How are we testing the system then? Okay, so I fundamentally disagree that we're never talking about the resistance, and that we're only talking about the voltage and current. That I don't know who you're talking to, but that isn't. It's just not. That's not the case. Perhaps the people you're talking to are never talking about resistance or other fundamentals, I guess. But that's just not true. One of the fundamental kinds of analyses of batteries is to do impedance on them, and through impedance you get resistances, capacitances, sometimes inductances. things of that nature. And it is actually quite common in my observation, in my experience personally, to discuss resistances, whether it's ohmic resistances, for instance, which are usually pretty low for a battery, and then charge transfer resistances related to specific processes, for instance, the SEI, the anode, and or the cathode. And then when you look at impedance of batteries, for instance, one of the most common kinds of analyses is to look at the resistance or impedance, if you will, same thing, right? Basically, of all of those phenomena and how they change over time. So, for instance, one of the common kinds of analyses that folks will do on lithium-ion batteries is to make a battery, do impedance on it at a fresh kind of a state, right? You'll get a charge transfer resistance, for example, for the SEI. Just as one example, it's usually at higher frequencies. As it is pretty low, it's a nice stable layer. You cycle it 100 times, do impedance again, and see how the charge transfer resistance changes. Usually it grows because the SEI starts to get thicker, and lose some of its effectiveness over time, let's just say. And so its resistance, its impedance can go up. And so those are ways, over time that the batteries deactivate or lose their reversibility and everything. And so in addition to the kinds of normal metrics of voltage and current, which usually translate to capacity, how many milliamp hours or milliamp hours per gram it's giving you, at what voltage, what power, all those kinds of things that you're probably referring to as far as people talking about the current and voltage. One of the things many people do actually very, very often, as I'm mentioning, is couple those analyses with impedance analyses to discuss, well, at 100 or 1,000 cycles, the voltage, current, capacity metrics went from whatever to whatever. They dropped by some amount. That is coupled with an increase in the impedance of the SEI and the anode, which correlates to a lower performance over time. Things like that. That's actually quite common. So I would encourage you maybe to, unless I'm misunderstanding your question, which is certainly possible, and please feel free to clarify if you're meaning something like why. Your question isn't. I'm not understanding it properly again, which does happen. But if just on its surface, based on what you're saying, if you're contesting that people don't talk about, the load or the resistance of a battery in terms of its performance, I don't believe that's true. I think that is actually pretty commonly discussed or observed, studied.
Oh. Like, do you think he's talking about like when people are studying batteries,
Mhm.
they're just looking at the battery itself, like what's like just as you were saying, the SEI, the internal resistance, things
Yeah.
like that. That's the study of the battery, but maybe they aren't studying the load of the battery. Like when you have the battery done, like in a mobile phone, it's drawing maybe current or voltage at certain like rates. It's like, well, when you have lots of apps running, it's drawing more current, or if you don't have a lot of them, it's drawing less current. And they're not studying that when he says, how are we testing the system?
That's a
Then
fair question.
maybe that's
So
part of
I'll
his
answer
question.
that because that could be what he means.
Mhm.
And you bring up a good point because I can't speak my knowledge of what you just described in terms of like consumer electronics or mobile
Yeah.
phones or laptops or anything of that nature. I am not aware of it. It certainly doesn't mean it doesn't exist. Which is take this for what it's worth. I am not endlessly knowledgeable about every little thing or I don't know, procedures or research topics, right? I am not aware of a kind of what do you say, like consumer electronic load mimicking test,
Mhm.
on batteries. What I am aware of, however, are car electric battery mimicry tests. That is a well-known thing that is done. So the kind of testing that people will do on batteries, for instance, that are used for EVs there's actually like, I think like in the US, there's probably different ones in different countries perhaps, or maybe the EU has one. I'm not positive, right? But I believe, like, for example, the Department of Transportation, like in the US, has uh it's like drive tests, or there's certain, and it's like there are tests to your point, which maybe this person, his question, tests that mimic what a car battery will do under a real load, let's say. So it's like super fast discharge, and then idling for a bit, and then a super fast charge, and then discharge. It's kind of all over the place. It's like crazy. Like it'll be like this up and down, like pretty long, stress test of the battery that is supposed to mimic what a car might be doing, where there's a lot of changes of charging and discharging at different rates, and it's something like that. So that does exist for the automotive kind of batteries for sure. I'm not aware of it existing like to mimic a phone, and perhaps it's because the use of consumer electronics is a little bit different. Like, it's not with a car, when you're accelerating, it's using a ton of battery right away, right? When you're driving at a constant speed on the highway, it's not using any battery mostly, or not much, right? That's when the alternator's charging the battery a lot. When you're idling, it's charging the battery. Like there's with a car, there's much more quick and varied changes of things. With your phone, it's generally trickling when your phone is idling, just like sitting here doing nothing, right? It's idling. And then when you're using an app, it's just sort of, it's usually like using battery at a relatively constant rate. Perhaps I'm wrong, and there's a little more variation in terms of like, well, now you open 7 apps at once and you're like live streaming, and then it's really crazy going. But like, for the most part, the battery usage in a phone is a little less erratic than with a car battery, which is why those kinds of automotive tests exist, right? Because if you're going to put a battery into an electric vehicle, it has to be able to like handle those kinds of crazy perturbations. And with a phone, I think it's a little different. So I'm not saying it doesn't exist, but I'm not aware of those kinds of tests for that application. I guess my experience is that most consumer electronic aimed battery tests, for whatever other way I'd put it, are sort of typical ones where it's just like, you just cycle it a million times, see how it holds up. You test these, you do impedance, you do galvanic charge discharge, and you just see how it holds up, or something of that nature. So yeah, I guess hopefully that kind of covers what was meant with those questions, with that question there.
Do you want to go to second question?
Yeah, sure.
This next question is, we say when current is 0, the system is in equilibrium. How is thermodynamics and equilibrium concept so important in electrochemistry, especially in supercapacitor and batteries context? Well, I can talk about it in maybe a more general sense. I feel like a battery and a supercapacitor are kind of, quote, non-equilibrium systems. Like, it's only when the battery's dead and not doing anything that the battery's at, quote, equilibrium. Because even like store-bought batteries will, if they're not used over time, they'll go bad, right? Like
they will, like any battery loses its capacity ever so slowly over time. Which kind of, by definition, to your point, means it's like kind of, I don't know how you would put this. Like, one way to say it is that when the battery is just sitting there doing nothing, not charging or discharging, it's kind of equilibrium, but in some sense it isn't, because it is actually slowly losing its capacity a little bit, like always, right? So it's sort of never at equilibrium. I'm not sure that the tricky thing, I want to let you discuss it in a more fundamental sense, but I'll add to that as just to further your point, is that in some sense we don't really use that term in the context of batteries, and perhaps that's why. We don't like, as battery scientists, I'm not aware of really using the term equilibrium much. It's not a concept that really, applies in a battery context.
And not that I read a lot of battery literature, but I don't feel
You're
like
missing out.
It's talked. I know.
A little light reading in the morning,
It's like look at this charge discharge plot. Oh, looks exactly the same as every other charge discharge
you
plot.
just don't get it. He doesn't get it.
So actually, one concept of equilibrium and thermodynamics, when we say that something's at equilibrium, this is a good description of it, but it means that the system can't do anything to lower its energy. Like when the Gibbs free energy is 0, we say the system is at equilibrium. That means we can't possibly get any more energy out of the system when it's at equilibrium. And in my mind, that's like, it's a dead battery. It's a situation like a battery that's charged and just idling, not doing anything. The chemicals over time, it might take years and years of an idle battery to eventually die, but it can lower its Gibbs free energy just over time. It just takes a really, really long time. So the concept of equilibrium, in that case, I just think of when the current is 0, the system is at equilibrium. We say that the battery or the supercapacitor is completely discharged. There's nothing that system can do to lower its Gibbs free energy or any by movement of molecules. It can't do anything to move the molecules around such that the energy gets lowered, which means you always have to put energy into the battery or the supercapacitor to give it charge so that it can do work. In a general sense, we use the concept of equilibrium just to describe things like redox reactions, the Nernst equation. We're looking at the concentration of different redox species, and I guess maybe I'll just share this slide of just the Nernst equation, because it is the expression of equilibrium that we kind of think about when it comes to electrochemistry in a general and just a broad sense. There's the potential of like an electrode. There's the standard redox potential of the reaction, and then there is the activity or concentration of your oxidized and reduced species. And we oftentimes use still this kind of formulation when we're talking about batteries and maybe not supercapacitors, because we're not talking about supercapacitors in this case because this is a Faradaic reaction. This is not a type of reaction that would occur in a supercapacitor, but this would happen in a battery. You do have electron transfer in this kind of sense in the reaction. So the potential is related to Gibbs free energy. The change in the Gibbs free energy is equal to N, or sometimes minus NF, and then E. So when delta G is 0, that usually means that your E is also equal to 0.
Actually, it means that F is 0.
F is 0.
Faraday's
right.
constant
becomes 0.
Stops existing.
That's right. So, and there's certain instances, we look at the E naught, which comes from thermodynamics when we're designing batteries. Like, the reason why lithium is used as a material is very much because of its redox potential. That's what gives it its voltage. So those are thermodynamic concepts that are used to govern or drive the way we think about batteries and battery science. But when we say that the current of the system is, or when we say that the system is at equilibrium, then you can't get any more energy out of the system. You have to move it out of equilibrium to actually get energy to get the system to do work. So I would describe it or think about it that way, at least in that context. Okay, moving on. Moving on. So Hasith asks, can I test my potentiostat circuit using dummy electrochemical cell? Yeah, you.
The follow-up. The follow-up
was
was
a follow-up.
It was more context. I have a homemade
yeah,
potentiostat device, but I don't know my results are right or wrong. What are the ways to solve this problem? I think those are probably related questions.
Yes. Yeah. Thank you. Well, yeah. The answer is yes. And your dummy cell doesn't even have to be something super complicated. Literally, you can just use a resistor. So if you have a 1 kilo ohm resistor or something like that, you can hook it up to your potentiostat in the 2 electrode configuration. You can do something like cyclic voltametry or bulk electrolysis. And because you know exactly what the load is, and it's just a physics resistor, you should be able, the results that you get should mimic what you would expect from physics. So in the case of a resistor, you should get something like, I should actually get a straight line. And actually, I tell people to test this. If you have a resistor as your kind of your circuit, and then you hook up, the working on one end. All right, so your working electrode of your potentiostat is here. Actually, that's a really terrible K. I'm trying to like finesse the K to look better.
Trying to
like,
get the right part to connect to the left part is just not behaving.
It's not
itself.
behaving. And then you have your counter and then your reference on the other side. These can be shorted together. And you can do cyclic voltammetry, voltage current, and you should get a straight line. You should get a straight line in accordance with Ohm's law, where V is equal to I times R. And when you get this straight line, you can literally just take the slope of this line, and it should give you the resistance. And that resistance should be equal to the resistance of the resistor that you've put in. That's the simplest way. You'll have little tiny deviations because resistors aren't perfectly resistive. And there's always going to be some minor detail issue, probably even in your software. But, if you have if you have a milliamp of current and you have a 1 ohm resistor, you should get like 100 volts or something. Or no, it's if you apply plus 1 volt, sorry, not just plus volt, you should get, you can even do this in the bulk electrolysis experiment. If I have apply plus 1 volt and I get 1 milliamp of current, then I should have a 1 kilo ohm resistor. And so if I put one here and I can just check, I can look at these points and make sure that, am I getting the right value? And if I'm getting something not this value, if I'm applying 1 volt and I'm getting a different current and I have a 1 kilo ohm resistor, then something's wrong with my potentiostat. So a resistor is the easiest and simplest dummy cell to work with. And then if you want, there are more complex, dummy cells that give you more complicated, like simulating electrochemistry results that you can then implement. But that's the easiest one to do. Easiest one.
Ankush in Korea has just some nice words, just nice to highlight. Hello, Pine Research Team. Congratulations on the 100th episode. I've learned a lot of things from you guys and hoping to keep learning good stuff from you guys. Wishing you both great health. We wish you great health as well. Thank you very much. It's just nice to point out positive stuff sometimes. So we appreciate you very much, Ankush. Best of luck to you and good health as well. And to be clear, last week was our 100th episode. We're gonna ride this fake 100 accolade as long as we can, probably until we get to 150, 200, maybe.
Oh wow!
We're gonna pretend it's been 100 forever, just to keep it going. I like celebrations, so
yeah,
I like it. It's cute. We're gonna keep it for a little while because I want to. And but otherwise, anyway, we appreciate the kind words. Thank you so much. And Mushshake has a similar thing. Congratulations on 100 episodes. He has some questions, but I'm just gonna leave it there. Thank you for the no, I'm just teasing. So thank you for the kind words as well. But what does it mean when a battery during discharge has a negative voltage? What makes it faulty? So what it means is potentially something very bad. So if you're discharging a battery and the voltage goes negative, you want to be very careful because you might have just caused a catastrophe to your battery. Possibly. I'm going to see if I can kind of illustrate what I mean. It's tricky in the context of a battery only because the exact voltages are unclear. I showed this example before with an electrolyzer. Let me see if I can bring up that. It might help kind of explain things in a similar fashion. It's not exactly the same, but it's analogous. It's circuit fitting. Let me pull up a slide here. I have to share the right one. Just give me a moment. I will get there. I promise. Okay, this one, and I want to get to this electrolyzer. Okay, no, I want the fuel cell. I changed my mind. I want the fuel cell. All right, here it is. All right. Let me share this slide. I'll try to explain what I mean and what it might mean when the voltage goes negative. So here, this is just proton exchange membrane fuel cell. It's analogous to a battery because it's a device that gives you energy, right? And you have an anode, right, and you have a cathode. So in a battery, you have an anode and a cathode as well. And the typical configuration, for example, with a potentiostat, I like to point this out, is that the working, I guess we'll do WRK, is on the cathode, and the counter / reference, I don't know why some letters are capital and some are lowercase, don't worry about it, is on the anode, okay? And so the voltage of the battery, if you will, is the working minus the counter. And so the working is 1.23 volts, right? And the counter / anode is 0, okay, volts. Okay, so I promise I'll get to sort of the crux of your question. I just kind of want to set it up so that hopefully it's clear. So the voltage or the potential of the cell, the fuel cell, the battery, if you will, is 1.23 volts. But it's also equal to whatever the potential is at the cathode minus the anode. All right. And so basically what we're doing is we are doing a reduction at the cathode. We're doing a oxidation at the anode, right? This is the same with a battery. So with a battery, we have a cathode and an anode. And what we have with a battery, you can imagine these being battery instead of fuel cell reactions. But the point is the same. When we are discharging, that's the designation of cathode and anode. Another way to think about it in a context of a battery is that the cathode is the electrode that is undergoing reduction during discharge, and the anode of a battery is the electrode that is undergoing oxidation during discharge. So it's what's happening during discharging. They do the opposite during charging. So the anode is actually going through reduction during charging. All right. What this means is that the E cell during charging or during operation, for example, on a fuel cell, for the reduction reaction to happen, E must be less than, let me draw it down here, it might be easier. So for the cathode, E needs to be less than E0, because that is just fundamentally for electrochemistry what drives the reduction. If the potential is less than the standard potential, the reduction reaction occurs. And at the anode side, E, let's say E anode, I'll put this here in E cathode, right? Needs to be greater than E0, okay, for the anode. This is for the cathode. So we have these two situations, right? At the anode, we want it to be greater. At the cathode, we want it to be less, okay? And so what we have here, forget about this, let's draw it down here. E cell is going to be always in this configuration equal to the E cathode minus E anode. Now, what this can mean is that it's the E cathode is less. So we had 1.23. So let's just pick a number less than 1.23 for this example. So this could be 1, right? And then anode minus needs to be greater than 0. So let's just pick any number. Let's just pick 0.2, right? 0.2 volts. All right. So E cell is 0.8 volts, right? So in other words, as the voltage goes down, I'm driving the reactions the way that I'm intending to. Now, let me think if I can relate this to a battery. The tricky thing about a battery is that the battery anode and cathode don't have quite so simple reaction. There's usually an intercalation reaction, and its voltage changes like a lot as you charge and discharge, but it's a similar kind of phenomenon. And what it can mean is that, I guess, try to think this through. I know I'm thinking on the fly as I answer this question, but as the voltage drops down, you start getting extreme um, let's just say losses of performance is one of the things that can happen. So for example, if the E cell here now starts to get close to 0 or even negative, at 1.23 volts, I have this reaction. I start to go more and more negative. I start driving this reaction more and more. But eventually, I might go so low, so I'm at like my E cathode is like, let's say like 0.2 volts or something. Well, at 1 volt, I'm only 200 millivolts down from 1.23. So I'm driving the cathode reaction. But if I go down to zero point 0.2, or let's say I even go worse, let's say I go instead, I go to, minus 0.3 volts or whatever. Well, I'm starting to go at the cathode side, even like I'm less than the E0 of the anode. Like I might start causing the anode reaction to occur at the cathode because I'm so far negative. So it's almost like driving the whole cell backwards. Like I'm doing the anode reaction, like the reduction of the anode reaction at the cathode, because my voltage at the cathode is so far negative, I guess. And then at the anode, it's a similar phenomena, right? I could go so far positive. So like, okay, I've got 0.2 and this is 0. Well, what if the anode reaction gets to like 1 or 2 volts? Well, now I might drive the opposite cathode reaction at the anode. Like it almost makes the cell operate in reverse, or like you can have other reactions occur. Like unwittingly, because the overpotential at each side starts to become so large that now you're not just driving the reaction of interest, you might be driving other reactions as well. Now, just to get to your point, so you had asked in the context of a battery. So in the context of a battery, what could those other reactions be? Well, some of those other reactions could be like the complete destruction of your electrolyte. It could be the oxidation or reduction of your material itself in like decomposing the like the carbon or the cathode, or combination with the electrolyte, and these are the things that can cause a battery to go into thermal runaway and start to degrade and things like that. So that's what we have with an overcharge or an over discharge condition. Now the how would I put this, the designation of 0 is arbitrary. So like for a lithium ion battery, for example, usually the lower limit is like 3 volts. The upper limit is like 4.2 volts. 3 volts is the voltage, the exact voltage is arbitrary. So it's not only that it's like, oh, well, if it goes negative, it's a problem. Because remember, it's always just the difference between the two. It's just that if you go too far in one direction, now if that boundary happens to be 0, then it's like negative voltage is a easy thing to observe, like don't let it go negative, right? And sometimes that is the case, where just the limit of charge is like 0 to 1 or something like that, based on the thermodynamics. But it's not guaranteed that like 0 or negative is necessarily a boundary. Voltage is arbitrary. I'm just trying to point that out. But the fundamental remains the same. If you go too far in one direction or the other, those individual voltages at the anode and the cathode start to get so far from the like standard potentials that you're no longer doing just that reaction. You're doing other auxiliary reactions as well. And that's when you start causing either the reactions to flip, like the anode one's happening at the cathode and vice versa, or just other reactions are happening, and your system can go into can have a lot of problems being caused with it. So so generally speaking, be very careful not to let that happen, basically. And then what makes it faulty, right? Like, I mean, honestly, short circuits can happen. That's usually what causes like rapid discharge or over discharge sometimes, is if you have a short circuit of some sort, or frankly, your software or your battery program, your potentiostat, your battery cycler, whatever, you didn't program it properly. Maybe you put like apply a negative current, discharge current, but you forgot your lower voltage cutoff. Like you should say stop when it hits 3 volts, right? And maybe you forgot that or something. Like these things happen when we're, learning batteries, and so we accidentally overcharge or over discharge a cell. And some of that just comes with knowledge of the software. So those are some of the things that can happen there, I guess. But yeah, definitely avoid if you can those kinds of things because like I said, you'll get some auxiliary reactions that could be very damaging.
All right. His next question, Moshe has another question. What exactly is the Fermi level of an electrode? Is it something only applicable for solid state batteries? It might be. It might not be.
Well, the Fermi level is applicable everywhere, right?
I guess it's applicable everywhere. It's just how far down the rabbit hole do you want to go?
Huh. Well, it's definitely a theoretical, electrochemical topic, and to that extent, it's applicable everywhere. Like you could talk about the Fermi level in any electrochemical context in some sense. I would say,
Yeah.
right?
Yeah, so I'll share this. This kind of is my. I'll do this relatively quickly, so it doesn't take too much time. But this is, if you want to know like what the Fermi level is and kind of like somewhat from first principles, this might be helpful. So, in basic chemistry, you learn about atomic orbitals, and so you have an atom, and that atom has filled atomic orbitals, and these orbitals represent wave functions, basically, of an electron. And then when you take that a step further from the atom and then you go into molecules, you get what are called molecular orbitals. So whenever you have a bond between two atoms, and I think just for some reason this slide like just messed up some of these things, but when you have these two atoms, they form bonds with each other and they form these kind of molecular orbitals. And molecular orbitals are also wave functions, just like the atomic orbitals, and they're considered these linear combinations. And what you'll notice on the y-axis is that we have just energy. So you can tell that the energy of some electrons in certain orbitals are higher or lower than other ones. And this can become more complicated, especially you get these bonding orbitals, you have anti-bonding orbitals, you have orbitals that are not assigned to, or you have electrons that are assigned to orbitals that are kind of non-bonding, and this is how we can think about and describe bonds between atoms to form molecules. Eventually, and another kind of interesting thing or caveat is that the bonding orbitals represent they represent a configuration of the waveform of the electron that has constructive interference between the two orbitals, and then between the two electrons. But then the anti-bonding orbitals represent a configuration of the waveform that is destructive, that it does not form a bond. So you get these bonding and anti-bonding orbitals. Eventually, moving up from kind of the atomic orbital, let's say you had a cluster of atoms. You had between 2 and like 1,000 atoms. Well, now you end up forming these kinds of it's not just single molecular orbitals. You form kind of this lattice, what we will eventually call a band of orbitals. And these orbitals here are also kind of in the same format as the atomic ones. They're these filled these filled molecular orbitals, and these unfilled orbitals or anti-bonding orbitals that don't have any electrons in it. And eventually you move, and there's a couple things to notice about these, is that the spacing, the gap between the orbitals starts to get lower, and the gap between the highest occupied orbitals and the lowest unoccupied orbitals also starts to get lower. So now, that's the atomic view of things, and I will get to what the Fermi level is. But we ultimately take this not just from one atom to 2 and 1,000, but to like a whole mole of atoms. You end up forming what are called bands, which is where all these molecular orbitals, the orbital overlap, the number of electrons, and all these things become so high, so dense, they form a continuous band, and you end up getting, in some cases, overlap between the anti-bonding and the non-bonding orbitals. So this is actually kind of what this is. When you have say a semiconductor, for example, you will have a gap between the bonding and the anti-bonding. In a lot of materials, you may have unfilled valence bands. But in most metals, you'll actually have an overlap between these kind of empty anti-bonding orbitals and the bonding orbitals. So the Fermi level in this kind of situation, this is the Fermi energy, is this level right here. It's the level of the filled orbitals that contain electrons, and it's the energy of an electron at this level. The Fermi level also, in the case of, say, a semiconductor where there's a band gap, is actually kind of in the middle. It describes the kind of 50% probability that you'll find an electron in this orbital. So that's the other kind of definition of the Fermi level. It's like Fermi energy, or the Fermi level, is the energy where there's a 50% probability that you'll find an electron there. So that's what it is for a band, for like the band gap. But when you have metals where these guys are overlapping, then, well, the 50%, there's a 50% probability you find something slightly above, slightly, 50% probability, here and here, where it's filled and unfilled. So right in the middle is what's the Fermi energy, and that's what the Fermi level is. And so you can use this for like semiconductors. That's where it's mostly actually used for, things like Mach Shakti and stuff like that. But for solid state batteries, that's also how it can work. So hopefully that makes some sense. I know it's very complicated, but the useful thing I have found with the Fermi level and Fermi energy from an electrochemistry standpoint is that the y-axis on that I was using was just energy. So you're describing the energy of an electron. Oftentimes, people will put like the potential of an electrode, and they'll move the potential up and down. So those are two different things, but they're related to each other. So Fermi energy looks at the energy of like individual electrons in metals that are the ones that are often used to do the electrochemistry. But the potential is like the driving force. So they're two different units. Don't get Fermi energy or Fermi level and potential confused or differentiate. They're technically two different things. But yeah, that's what the Fermi level is. Okay. Let us know if you have any like further questions or clarification on that. It took me a while to wrap my head around what the Fermi level was from like first principles, which is why I shared with you.
I like that you explain that, because I have a trouble explaining that properly.
Yeah, it's
tricky.
It is tricky. And then what makes it weird is like all those things. It's like, oh, are there actually like little levels that like the electron sits in? It's like, no, it's a wave function. That's what it is. It's the energy of a wave function.
It's all made up, because electrons are like the Schrodinger thing. It's like they may or may not be somewhere. There's a probability, but we don't know anything about where they are. We just guess.
Mhm.
I'm half kidding, but that's kind of the gist
Kind of a bit of it.
how we approach electrons, which is very weird. But hey, that's what science is all about. It's making up stuff that's weird, and I don't know what the point of that is.
Anyway,
that's pretty cynical. Science is better than that. All right, moving on. Anyway, Ahmed says, can you explain why the resistance for the SEI becomes greater than the charge transfer resistance from EIS measurements for a lithium cell utilized for investigation of novel electrolytes? I was going to say an answer, but I realized you're talking about a lithium cell. I am wondering if you're misattributing.
Oh, in the EIS,
in
you're
your EIS,
mislabeling
the SEI, because
yeah.
frankly, I don't know how much of an SEI you're going to get on just a lithium cell. I guess it probably forms one, but SEI usually forms on carbonaceous materials. I guess it probably forms in other cases as well. But one of the things that might be happening, and it's again, it's a little more common, I guess, like if you have graphite anode, now you have lithium. I know you don't have graphite, but one of the things that can happen, for example, that sounds like a good thing, but actually isn't a good thing, is that you can have secondary storage in the SEI, which is to say, over time, initially the SEI forms, and it's like a thin layer of like decomposition products on typically the anode, but if it's a lithium cell, it'd be on both sides. And a little bit of it forms on the carbon as well, but it's a layer of like slight decomposition products from the electrolyte that forms on the surface of the electrode, or the anode or the cathode or both, that in and of itself is protective in some fashion, preventing basically like the high voltages of the battery from causing more electrolyte to be ripped apart like continuously, something like that. But one of the things that can happen over time is that you can have what's known as secondary storage in the SEI. And so it's kind of what it sounds like you think about the anode. The anode is the side that stores the lithium metal during charge. So if you're charging up a lithium ion battery, lithium ions are entering the anode. That's the reduction reaction during charging. And lithium ions, whether they're intercalating or it's a conversion reaction or an alloying reaction, lithium ions are joining into the anode, the material, the carbon, the silicon, whatever it is, right? But another way that they can sort of stick or join in the anode side, again, it could be both, but I'm just sort of describing it in the anode context, is that they can join into the SEI itself. And I don't know precisely how, if people have imaged this or quantified this per se, but in some sense, there's secondary storage in the SEI that we know can occur. And so lithium plus, like, in some way, is like hanging out in the SEI. Now, this sounds great. Oh, I get extra charge capacity. It sounds kind of good, but it's not, because it's not really stable, and it's not the mechanism you're trying to study, and it's not really necessarily repeatable or predictable. And it can also lead to the SEI becoming thicker, possibly collapsing. Like if the SEI grows and becomes too thick and isn't sort of in a stable thickness and state throughout charging and discharging, it can collapse or again become really thick, and if it collapses, the whole battery can kind of die or go into thermal runaway. But if it becomes thicker, this gets to the crux of your question, which is one of the possibilities, which is that over time, if the SEI gets thicker or is involved in secondary charge storage, that thickness can increase its resistance. Now, I guess in some cases, perhaps that phenomenon can lead to its resistance becoming greater than the charge transfer resistance of the electrode itself. And I would suspect, possibly in your case, it might be because you're using just lithium metal, which has a really low resistance for intercalating itself. That's one way to look at it, right? So like having lithium plate on lithium is a pretty generally easy process. Like you reduce on one side, you oxidize on the other. One side's giving up lithium, the other side's just accepting more. It's one of the reasons why lithium in general as a metal by itself is not the greatest choice for an anode. Because you might ask, why don't I just use lithium all the time in batteries? And we don't, because one of the facile natures of its intercalation, deintercalation process is that it forms dendrites pretty easily, whereas other materials don't. And so part of that process might mean that its charge discharge characteristics and resistance is relatively low. And if you're starting to get some of those effects, thickening or secondary charge storage in the SEI, that might lead to the SEI being growing in that way. The other possibilities are simply that you might be misattributing the peaks or the semicircles, in your Nyquist plot, and you might be tricked into thinking the SEI is growing, and perhaps that's actually just the anode or some other process. You might be. I'm not saying I don't obviously know. I'm not looking at your data. I'm just throwing it as a possibility. It's possible that you are assuming what is the growth of the SEI is actually something else, or partly another thing. And then the other last thing I'll say is that there are cases where either in conjunction with what I just described, with this SEI layer thickening, secondary storage, things like that, or just due to the aging and testing of a battery, that some of the semicircles will like mesh together because their time constants become somewhat similar. And so it looks like a semicircle grows or becomes really big over time, but really it's just that like the SEI and the anode, or the anode and the cathode, they used to be like two distinct semicircles, and now they were like meshed into a super semicircle, like a super monster, amalgamation in your impedance plot. That can happen. And so in those cases, you need to do something. If you want to differentiate between the processes, they're occurring at two similar time constants. And so they're like one semicircle instead of two. You got to do something like DRT, distribution of relaxation times, sometimes is needed in those cases to like determine how many charge transfer processes you actually have when they're a little bit indistinguishable in the Nyquist plot. So that's hopefully some food for thought for you on those that phenomena.
Looks like Ahmed has another question. He's asking, when a metal is dipped in electrolyte, it has a negative surface charge due to metal dissolution and electronic accumulation. But what is the physical meaning behind a positively charged metal surface?
Well, it depends on what the potential of its dissolution is, right? Like,
negative charge,
or what the reference is. So those are two things. I would say, like, not every metal has not every metal or species has a negative potential for whatever its process is, or a positive. It's all over the place, right? It depends on the metal. So some will give you a positive sort of natural potential, and some will give you negative. And then it depends on what your reference electrode is. So if you're saying, oh, it's a negative potential, but it's like, well, your reference electrode is just different.
Well, there is. So if you just had a piece of metal not connected to any, this is like the fundamental, like if I just have a single electrode
What's
system,
its potential, right? Yeah.
What is its potential? And I'll draw this this thing. So commonly, so this is the situation where if I have, so I have my beaker, I've got some water in it, and then I just put a piece of metal in here. And then I have and there's some electrolyte, right? There's some plus and some minus charge. Actually, I'll draw it. Yeah, I'll draw it this way. Plus and minus. So there's some plus and some minus, some plus. Yeah, so I have electrolyte. So the way we think about or look at these, at least the way I do, is that there is the electrode here. And the electrode has what's referred to as the inner potential, which is similar to the Fermi energy. So there's a phi. Oh, God, I can't draw phi. I can't draw anything.
K's and phis.
K's and phis.
It's only the letters, though. You can draw diagrams great. Letters are hard, though.
Letters are hard. Even my diagrams are still whatever. It's okay. And this is in solution, and there is a potential of the solution, and the potential of the solution, and the potential, and what do these potentials mean? The potential in this case just means if I, the potential of the metal means that if I have an electron or a charge, from here, to here, it's the energy required to move it from here to here. That's what the potential represents. It's like the energy to move a point charge from this place to this place. And throughout the metal, it's easy. There's like almost no energy required to move charge around because it's super conductive. Right? It's just like really conductive, very easy to move it. But it's much harder. It's a higher potential to move an electron around or charge through a solution. But when you have at an interface where you have two dissimilar potentials, they tend to even themselves out. This is the formation of the electrical double layer. The potential as it gets close to the electrode surface starts to change. And that's the same here. So what happens is, because electrons are so easy to move in a metal, you have so many charge carriers, you have tons of charge carriers, it's very easy to say, oh, well, I will build up negative charge at the electrode surface to balance the difference between these potentials. And I'll build some positive charge from my metal electrode to kind of cancel that out. Because I can't just have these two disjointed potentials here. There needs to be kind of a continuum, if you will, of potential between the solution potential and the metal electrode potential. And this is where the charge comes from, because it only happens when there are these two dissimilar potentials that you'll start to get charge buildup of one or the other. And so that's kind of why you get charges. That was ultimately what his question is. What's the physical meaning behind positive charge on the metal surface? Well, this is kind of the physical meaning of it. The charge, so the negative charge here are anions. So they're anions. They're also dipoles. You can have like a water dipole that's let's see, I think you draw it this way, right? So you draw the water dipole this way. That's negative charge towards the electrode. And what are these charges on the physically? What are the charges on the metal? Well, it's just electrons are just not there. I just move the electron over here. So I have a bunch of electrons, here and here and all over the place. But I just moved a little bit far away. But because there's so many electrons in a metal, it's kind of crazy to think about it. There's like compared to semiconductors or insulators, there's like compared to a semiconductor, there are 7 orders of magnitude, like 10, like at least a billion or 10 million times more electrons in a metal than a semiconductor. So it's very easy to generate charge at the electrode surface just by moving the electron like boop, boop, boop. It just moved it a little bit. That's what it physically.
Is that the noise it makes?
That is the sound that it makes when you put the metal in here. You hear you think you hear a splash.
Yeah,
usually the splash drowns it out, but there's a little like
boop. There's no splash.
Yeah. So you have to do it very, very, very quietly. But when that happens, there's a little boop. That's what happens. That's the sound of an electron moving just like 1 or 2 atoms away.
That's amazing.
I had fun with that.
Yes.
But yeah, hopefully that kind of hopefully that gives you a little bit of a better understanding about, like, that's how I think about physically what's happening on the surface when we say like, oh, there's positive charge building on the metal electrode and there's like negative charge building on the solution outside of the metal. So doesn't look like there's any follow-up on that so far. So I think hopefully Ahmed is good.
Yes, I think so. Where were we here? We're at
I don't know how to answer this next question because I don't know anything about it. I don't know if you do. Zaki is asking, in electrochemical noise analysis literature, I read of low pass filters. Do they come integrated with all ZRA potentiostats or need to be sourced separately? I don't know enough about electrochemical noise analysis.
Well, so with a electrochemical noise measurement, you are trying to use a relatively high low pass filter if you can. To the last part of your question, I can speak for our company, Pine, of course, and I would assume it's a similar phenomenon for every other major commercial potentiostat manufacturer. Let's just broadly use that term. Low pass filters are part of every potentiostat, I would assume. Ours have the same. The filters, when you talk about filters of data, of potential and current, basically, but usually it's current, more, specifically in most cases, they use what are called low pass filters, which is what it sounds like. It filters out stuff. Like if you have a 1 kilohertz low pass filter, it means that it filters out frequencies or perturbations greater than 1 kilohertz. And it allows low pass. It allows lower than that to pass. So when you're looking at a filter, if you want to look at like cleaning up your data, you can apply a very low frequency, low pass filter. So something like, I'll just go to an extreme example. A 1 hertz low pass filter would be the cleanest looking data you've ever seen. It would also probably be terrible because if you're studying a reaction, you're doing cyclic voltammetry. And it's like, it sweeps up and makes a peak like in less than a second. Like, let's say it's like whoop and whoop. It's like the electron transfer, right? It goes whoop and makes a peak.
That's the sound of
That's the sound it makes, right?
Yeah, that's the sound it makes.
and it makes a peak in less than a second. If you have a 1 hertz low pass filter, and that feature, that movement or perturbation is faster than a hertz. If it's like 2 hertz, it's like half a second. It goes up. It's going to filter that out. You're going to lose that data. So this is the point of a low pass filter. It's like, okay, well, I want it to be smooth. I want my data to be nice and smooth. But if I use too low of a low pass filter, I'm going to filter out the features I'm actually looking for. So that's a bad thing, right? When it comes to something like electrochemical noise, you're talking about probably kilohertz range noise, so to speak. And so the idea of using a low pass filter, if you're probably always going to have one somewhere in your potentiostat or whatever. But if you're doing ZRA to get electrochemical noise analysis, you probably don't want to have a low pass filter because you need the noise. Then you're doing something like the what is it, MMS, MI, what is it, MIS, MI, maximum maximum entropy, MEM. That's what maximum entropy method, or discrete Fourier transform. Basically, the electrochemical noise analysis, which is it's a little wonky in my opinion. It's a little weird. Like you're just taking noise and you're kind of doing like almost like a statistical analysis of it, deconvolution if you can, to look for peaks in and see if there's any sort of characteristic kinds of peaks that are indicative of corrosion. That's usually what it's done for. But if you filter out too low, you're going to miss all of it. Like and that's the thing. Like most of the time, the low pass filters are trying to get rid of noise. Well, with the electrochemical noise measurement, you are literally only studying the noise, so you don't want to filter it out. So if it seems like your question is kind of asking about like trying to get a low pass filter, and it's almost like you want to make sure if you're doing a ZRA measurement that if it's applying a filter, like a low pass filter that's like 100 hertz or something, you got to ramp that up probably to at least some kilohertz, I would imagine, value. So you're not missing all of the actual noise with which you're trying to analyze. That would be my take on that. I don't really know of cases where you would like source a separate low pass filter to like add to a potentiostat or anything like that. I'm not really aware of that most of the time. Like I said, commercial potentiostats, and I can speak for Pine, like we have all of our potentiostats come with low pass filters, and there's usually like several options. It depends on the potentiostat, of course. Some have more options than others, but there's multiple different options for the filters that you can apply at any moment. And there's usually an automatic, selection of some. When you pick a CV, it picks a filter that would make most sense for most applications. You can change it if you want to. Those kinds of things are part of our potentiostats and software. But that's just what I would say to that, I guess. Just be careful if you're, again, if you're doing a ZRA measurement for the purpose of electrochemical noise, that you're not picking a low pass filter and losing all of the data that you're trying to make. So just I would caution about that.
All right. Next question. We have, I guess, 2 questions from Hasith. He's asking, what are the affected reasons to peak difference and some peak current? Some peak current can see more negative voltage side. Some peak current can see more positive voltage side.
I think it's like asymmetrical, like your CV has like a higher peak on the oxidized side than the reduction side, something like that.
Something
of that nature.
It might be. Saying some voltammograms show more than one oxidation peak and reduction peak. What are the reasons for that?
EC reaction. EEC reaction, something like that. I mean,
Yeah, I mean
that way you see like 2 reduction peaks, 1 oxidation if there's a chemical reaction.
Yeah.
I don't know if
could
you want to simulate or not.
Yeah, I could try to simulate this. I am still trying to understand a little bit more, like the first part of his question about some peak current more negative, some peak current more positive voltage side. I'm not 100% sure.
I'm guessing. I'm gonna see if I can simulate this as well, because I think I know what he means, and I'm not sure if what I'm gonna try will simulate that or not. Yeah. So here, let me propose a solution. I don't know if this is the answer, but here's our simulation software, Aftermath, Blue Aftermath Live. I'm guessing what you're talking about is something like this. This, if you see the voltammogram here on the left, on the right, because left and right is hard. Maybe you're looking at something like this, where it's like I have a really high oxidation peak and like a lower reduction peak. So, for example, this is like a standard CV, like, oh, look, nice, perfect looking CV, one peak, and they're the same, right? Well, all I did to get what I just showed you was I changed the diffusion coefficient of 1. Okay. So I don't know if this is like exactly what you're seeing or this is the perfect answer, but let's just say if you have um, uh, uh, a peak, an oxidation and a reduction peak in a CV, but the oxidation side is bigger than the reduction side, for instance, it could be either direction, right? One way that I've made this happen, which leads to the explanation of why is this happening. Well, in this case, A is reducing to B with a 1 electron process, but in this case, the A species, for whatever reason, has a much smaller diffusion coefficient than the B species. And so what that leads to is a much lower and more broad, I guess, like Cottrell diffusion characteristic on the reduction side than the oxidation side. And so what it looks like is like an uneven peak, uneven amount of current on the peaks. So I just wanted to throw that out there because I don't know if that's precisely what you mean, but that's just one. It could be mismatched diffusion characteristics, so to speak. And then again, to your other point, like what happens if I have, I don't know if this will show precisely. I'm just going to see if this even gets me towards what I'm looking for. If I have like multiple peaks on one side, but fewer on the other side, this is a ECE. Let's see if I can make that happen by just doing this. I think this might make one of the peak go away. Maybe it won't. Yeah, kind of. So here I got two reduction peaks, but only one oxidation peak. And the reason for this is that I just made up an arbitrary reaction mechanism where I have A goes to B, an electrochemical reaction. And then I have this chemical step where B can go to C. And then I have another reaction where C goes to D. It's like 3 reactions, right? And the only thing that's keeping me from getting this last peak is because the chemical reaction I have driving extremely fast. Like it's going, like all of the B is going to C. So I don't get this last oxidation step because once the B shows up from this oxidation, it all is chemically reacted. And so I don't get my last peak. So that's just, those are just 2 answers. If those are what you're getting after, I don't know. But as 2 direct possibilities, let's just say if I have, more than one, a different amount of oxidation and reduction peaks in my CV, it could be because you have a chemical step eating up one of the reactions. That's one possibility. And then if you have too much current on one side or the other, it could be a diffusional mismatch, like the diffusion coefficient of one species being much bigger than the other. Those are possible answers to your question, I guess. I just
yeah, it's like a lot of things could be happening.
Yeah, for sure.
To a degree, I feel like we almost have to see the voltammograph, know more about the electrochemical system to really know.
I just thought the simulation would be a way to show
with
numbers, just here's 2 possibilities that could be the thing for you. But yeah, if you have a follow-up, please feel free to let us know. I don't know if that's exactly what would answer your question or not. So
absolutely. Anya asks a question. Ayana asks a question: is any material SC used for hydrogen production? I asked the follow-up to him, what does he mean by SC? I don't know what that, if it's an acronym that refers to something.
Is it any material used for hydrogen? I don't understand the question. Used for hydrogen production?
Yeah, I mean, there's certain materials used for hydrogen production on like a commercial scale. You can electrolyze water with a variety of different electromaterials to produce hydrogen. But some materials won't work. Some materials are easier or harder than others. But I don't know what you mean by SC. So Ayana, if you want to provide us a little bit more clarification about your question, we can talk more about it. But I I think we need to know a little bit more about what you're asking. Tiki is asking, what is the physical meaning of charge-discharge test? What is the significance of it? I think the charge-discharge test is just to it's just to test the battery, how well the battery works.
Physical meaning of the
Physical
charge discharge. I
meaning.
mean, it's to test. Yeah, I mean, well,
Like its stability, how long, you want to do multiple ones of these charge discharge tests to see what the performance of the battery is over so many cycles. Does the voltage, does it take longer? Does the voltage, not reach the voltage it's supposed to in a certain amount of time? The amount of current that you get. That's my kind of take on it. I don't know if they're, and to a degree, you can observe, at certain charge discharge cycles with different batteries constructed differently or different materials, maybe you get either you observe that, I get a little bit more resistance, or I don't, it doesn't reach the same potential, or it reaches the potential much faster after 50 cycles versus another one that's like 100 cycles or so. Maybe the battery is degrading a lot faster. But it's all about stability, I think, at the end of the day. I don't know if too many people gain too much in the way of physical insight about their battery from the charge discharge test. They're literally,
I mean, other than just like if the charge discharge doesn't go well,
yeah,
physically one or both of your electrodes might be like degrading or decomposing or not performing properly. But yeah, I mean, a lot of that kind of physical stuff you'd have to use like impedance or like
mhm.
microscopy, like analysis of the materials afterwards, after a charge discharge test. Other than just the general physical explanation of like, you're looking at how well lithium is stored in each side. Like a battery is something that passes ions back and forth, basically. Usually, lithium or sodium or zinc, whatever the battery is. But for like lithium, it's like passing lithium ions between the anode and the cathode. And a charge discharge test is studying how well each side stores and releases its lithium during whichever process you're studying. So yeah, that's basically it.
Yeah.
And this next question looks like maybe it's
Mhm.
somewhat an
Same.
extension, I guess,
Yeah.
but why is current kept constant and potential varied in a galvanostatic charge discharge technique? And what information can it give me about the system? Practical insight. So the explain this in a accessible or general way.
Like the rate of charging is more important than the limitations of the charge itself.
Yeah, something
some
like
ways.
that. The current, remember that current is the flow of electrons, right? The unit of current is amps, which is coulombs per second. So it's the amount of charge occurring per time. Okay. So it's a rate. Current is a rate. When we are charging something or discharging something, we are extracting energy from it or putting energy into it. From the perspective of a charge storage device like a battery or a supercapacitor or whatever, fuel cell or whatever, the energy that you're putting in or taking out occurs at a rate, right? We can take energy out of it. We can put energy into it if we're charging or discharging. And there's a rate at which we do that. It is simply more, for a variety of reasons, practical and a better idea, let's just say, very generally speaking, to control that rate at which we are putting energy in or out. And so that lends itself to controlling the current rather than the voltage. If we control the voltage instead, you can charge up a battery by holding the voltage somewhere and forcing it to charge up or discharge. It will not be at a constant rate. It will change in the way that setting the voltage causes the current to decay, like the current is changing all the time. And so the rate at which you're charging or discharging is changing. We are often looking for characteristics of battery materials based on their charge discharge, how well they handle being charged and discharged over many times, right? And to control the rate at which that happens makes a lot more sense, because we can say, well, my battery is behaving well or not well after being charged up and down 100 times. But if it's all over the place, like the rate at which that's happening, well, how can I know if that's just because my ability to control the rate is not helping and it's causing it to degrade faster? Or I can control the rate by controlling the current and say, okay, well, I'm charging it up at this exact rate every time. It's very, very slow or it's very, very fast, whatever, but I've chosen a rate, right? And then it allows me a little more control. It allows me a little more standardization to compare my results and observe those kinds of characteristics. So with a charge storage, device like a battery or a supercapacitor, controlling the current and controlling that rate makes a lot more sense than controlling the potential or the voltage of the cell, let's just say. So I hope that kind of answers that question for you there. So,
all right, very good. And moving on, Tanmay asks, can you explain standard hydrogen electrode? Sure. So this is what's often referred to as the SHE, standard hydrogen electrode. Often it's confused with things like NHE or RHE, things like that. One thing to note about the standard hydrogen electrode is it's actually a theoretical potential. So the normal hydrogen electrode, for context, is the potential of a platinum wire in 1 molar and 1 normal of a acidic solution, so sulfuric acid, hydrochloric acid, with 1 atmosphere of hydrogen gas being bubbled into it. So when you have that electrode, it's very good. It works. It has a defined potential in our system of 0. But there can be interactions that adjust that potential, such as the nature of anions or the anion that you use, if it's a chloride or a sulfate, if that interacts with the platinum at all. So there are things that can affect that potential. So the standard hydrogen electrode, by contrast, is a theoretical potential, and it is the potential of 0. It is, I'll just kind of draw it out here on another page. But the equation, just very simply, the reaction that governs the SHE, so this is SHE, the She electrode, as Jerry Body likes to call it, which I think is great.
That's cute. She electrode.
And I guess it doesn't matter which direction you're going, but we usually have electrons on the reactant side. So 2 protons, solution, plus 2 electrons are in equilibrium with hydrogen H2 as a gas. And so actually the potential of this, if you really wanted to, so we define this as 0 volts. Let's get that a little bit closer. So this is what we define as 0 volts. And it's actually kind of like, bless you. The potential equal to E naught from the Nernst equation minus RT over NF. And that's natural log. It's actually, in this case, it's the pressure of hydrogen gas. There's still activities, but it's really, in this case, a pressure. And then I believe it's concentration of H plus. I think it's H plus squared. Never remember. I think it's raised to the exponent.
Coefficient goes. Yep.
So this is like the expression, and when you have, ideally, again, this is theoretical, but practically speaking, you have 1 atmosphere, and then you have 1 molar And when you plug these guys in, the value of this gives you 0, and you're ultimately getting your E naught is equal to this guy. So that's what the standard hydrogen electrode is, and it's the kind of reference potential, if you will, that everything is kind of referenced to. So for aqueous systems, we reference everything to the standard hydrogen electrode. So hopefully that makes sense. If you want a little more clarification, we can talk a little bit more about that. So yeah. Okay.
Variog has a question. I'm not sure we can really answer because we need to see the data for sure. But it says, I got a CV of cobalt-crystal solution with an oxidation and a reduction peak, but I've used acetonitrile, I assume that's what ACN means, as a solvent, and TBAPF6 as a supporting electrolyte. What is the significance of the graph? Well, yeah, I mean, generally we'd have to look at the graph to know what you're referring to, but it doesn't, nothing you're describing sounds like out of the ordinary in general, I suppose. I guess I don't know enough maybe about like a cobalt, what is specific cobalt system that you're using. I may not have knowledge of that or enough details about that, but like acetonitrile with TBAPF6 is perfectly like normal and common to use. So I guess I don't understand why, just in a vacuum here, like why you're questioning, like what is the problem here? And again, I guess as a very broad statement, we'd probably have to see the CV to know like what your confusion is, or something like that. I guess I don't know
Like-
totally how to answer.
Like if you're not an electrochemist and you're just a synthetic inorganic chemist and you've never looked at a voltammogram before, because that's what you have. You have a CV, a cyclic voltammogram. You're looking at the redox potential, if you will, of your cobalt complex. That's what most people are looking for when they just have a cobalt crystal solution. They get an oxidation and reduction peak, and for the most part, you can say halfway between the oxidation and reduction peak is approximately the formal potential of your cobalt system. Now, we don't know anything, as Neil said, about your reference electrode, your counter, your working electrode. We don't know. We don't see the graph itself, so we don't know enough about its significance. We also don't know if you have a lot of peak splitting, but there's a lot of information contained in a cyclic voltammogram. And indeed, questions we may even have. You can actually learn a little bit about the rate of the electron transfer. You can get some insight into that. But most people are just looking at redox potentials. And so if you synthesized a different cobalt complex with different ligands, then the redox potential may shift ever so slightly, maybe by 100 or even 200 millivolts. And there's some interesting chemical insight into that. Your ligands may be withdrawing or pushing electron density onto the metal center. That's making it either easier or harder for that oxidation or reduction reaction to occur. So those are just some hypotheticals, if you will, about what you can learn from the graph, from the cyclic voltammogram. But to a degree, we don't actually know all that much about what you know about electrochemistry to start with. But that's usually what people are looking for. Like, what's the redox potential of their species? All right, moving on. We're getting some more questions. Hasif has a question. Can we control the diffusion constant of any analyte? Generally speaking, no. The diffusion coefficient is a function of the analyte. It's also a function of the electrolyte solution it's in. So if you have a big bulky molecule, for example, it might diffuse very slowly. It takes a long time for it to move from one place to another. Similarly, the electrolyte solution that it's in, maybe, I don't want to use the word viscous, but it might be hard for it to move through. That's another thing that's going to affect the diffusion coefficient. So there's not much. So unless you're chemically changing your analyte so that it has like smaller, ligands or something, or if it's not as big and bulky, then you can tune your diffusion coefficient. but the diffusion constant or diffusion coefficient is an intrinsic property of the analyte itself. So it's not necessarily something, and of course the surrounding electrolyte, but generally speaking, it has a lot to do with the analyte itself. That's the only thing it can really do to affect its measured diffusion coefficient. So hopefully that makes a little bit of sense. Let's see. Let's keeping going through. Merkkan says, thank you about the emails for question on the last live stream, and it was great. Exchanging ideas were so valuable to me. Great. I'm glad that it was helpful. Best of luck. You had a very complicated CV. I thought I could provide some insight, but it was a lot. You know, you have a very complicated system, so I can't say I blame you for asking questions. But yeah, good luck. Good luck to you with that system and trying some of those control experiments I recommended. I don't know. I don't know how to answer the next one because I haven't looked this kind of stuff up. But Tribal DeBly, I'm just gonna call him Tribal. Tribal was asking what's Faraday's law, and then he's also asking what's Faraday's second law.
I'm more familiar with just Faraday's law of electrolysis as a general thing, which is that it's just, I mean, you just sort of use Faraday's constant. I know I'm not for a moment because I'm just thinking about this. Yeah, maybe I'll share. So I guess I don't, from a fundamental education class perspective, Faraday's constant is 9645.3 coulombs per mole of electron. And so what we do, is we have A plus an electron goes to B. We can Faraday's law and Faraday's constant comes from Faraday's law, which is that we can relate the current that passes to mass, basically. So let me think here. We have a certain amount of current that passes, and that's equal to basically Q over T, right? So essentially, if we have a certain amount of current over time, you can think of it as the integration. But if we just assume it's constant, current times time is equal to the charge, right? And then Faraday's law relates charge to what is it more specifically? Charge to So I mean the sort of direct reading of it here, I'm just reading sort of definitionally here, is that the mass of substance deposited onto electrode is proportional to the charge, basically, and that the proportionality is essentially Faraday's constant, something like that. It's like more we use more practical electrochemistry than looking at this kind of educational application of it. But we would say, for example, we have Q coulombs, for example, and then we would divide by F, 9645.3 coulombs per mole of electrons, right? So this would be the Q over F, basically, gives us the moles of electrons, and then we can use stoichiometry to say 1 mole of electrons gives me 1 mole of B, essentially. And so that allows us to get the moles of B that are formed. So this is like the practical application of Faraday's first law. And then his second law, I think, is more about the valence. So if B is 2 plus and A is 3 plus, goes to, like, if this is like an iron redox or something like that, there's a concept of equivalent valence or equivalent mass, and that's the molar mass divided by the valence. And so that's used in like corrosion electrochemistry.
Mhm.
I'm not like the most familiar with these laws, like in an academic sense
Mhm.
for applying them. But what I just showed you is sort of more broadly known as Faraday's law of electrolysis, like just broadly applied, which is that you get the charge either by integrating or multiplying current times time. You divide by Faraday's law, you use stoichiometry, and you can get the amount of species. That's the application of it, which is to say you're relating the amount of current or charge passed to mass or moles of species deposited or removed, basically. And Faraday's constant in Faraday's law is the bridge between mass and current, basically, or material, I should say, whether it's moles or mass, between material and current passed. That's what Faraday's constant in Faraday's law is used for.
Mhm.
So it's a little more of a practical answer for you. We're not professors, so I'm a little less equipped to like explain it from first principles, I guess I would say. But that's the more practical application of Faraday's law of electrolysis, I guess. So I'll try to leave it there for you.
Mhm.
Anderson is next, I think.
Mhm.
So he says, "Hi guys, how could I choose the correct parameters into a potentiostat in order to do CV, CA, and EIS?"
It's a bit of a
it's
ambiguous question because, well, one thing is, it depends on what your experiment is. We in our software, we have like an autofill button that gives a best guess as to the parameters used in CV, CA, and EIS. But you will always need to adjust the parameters based on your particular electrochemical system, and your specific needs. So in chronoamperometry, most of the time you're just adjusting the potential and the time. Just two parameters. The potential, you want to pick one that's way above the oxidation or the reduction reaction that you're studying. And the time, you actually don't even have to have it go for that long. Just a minute is fine if you're just doing a Cottrell plot, or even just a few seconds. For EIS, you typically might want to start at 1 megahertz, but you may find that you can actually start at 60 kilohertz, or 50 kilohertz, and then go all the way down to like 1 hertz or 100, or sorry, 100 millihertz. As you're looking at your system, the whether it's potentiostatic or galvanostatic will depend on your system as well. So the parameters will always be a function of the electrochemical system that you are studying as well. So it's hard to say in each case, okay, well, how do I pick the right ones? It's oftentimes a bit of trial and error if you're doing this for the first time. But ideally, you start with some experiment where there's some if you're do something in the literature that's already been done, and you can look at the voltage range, for example, and you can look at how much current they got, and you can say, oh, I can set my range and the potential sweep limits based on this paper that I read where this is where they were sweeping between. So that's, or in EIS, you can look at the approximate like range of, they may say the range of frequencies. They may also just have a Nyquist plot, and you can kind of say, oh, I should get an impedance around this value. And then you may have to play with like whether it's potentiostatic or galvanostatic EIS for that system. So sorry, I can't give you like a more like, this is like step by step how you pick the parameters, because it really does change from system to system with what you're doing. If you do have like a specific thing, like, oh, if I'm studying this, how do I pick the parameters? Then I can do that. All right, so we're gonna go in order of questions that are asked. So if you've asked a question, we are getting to them in the order that they were asked. So if you're looking at your question, we have some that have come ahead of you. Azim is asking, can you talk a little bit about the electric field distribution between two electrodes as well as electrical double layer during water electrolysis, considering hydrogen bubble sitting on the cathode? That's a very good question, because when you have a hydrogen bubble sitting on the cathode, it certainly will affect the electric field distribution, because you effectively don't have one on that bubble. Um, but I mean, I can talk generally about electric field. Like, usually when you have a conductive electrolyte, your electric field with enough supporting electrolyte is very, very thin. Um, it doesn't expand outwards from the electrode. But when there's a bubble sitting on it, I think the field basically goes away. You have a potential there, but you don't necessarily, like, you can't do any electrochemistry. It's got to be displaced, and solution comes up. So I don't know any like studies or anything like that where someone's looked at the field effect of having small bubbles on your working
I wonder
electrode.
if it would just cause a distortion, is all I could think about, because like the field is probably regular or uniform or whatever you want to call it between anode and cathode, for instance.
Mhm.
And even through the electrical double layer, like the field is going to be just, but it's like, because it's all liquid,
Yeah.
like there's electrolyte in between the two. And so the field is going to be just happy in some fashion between the two. But when you have a bubble, I just wonder if it causes any distortion because
Yeah.
of the different phase. Like, does the field proceed through gas unimpeded, or does it go around? Like, are there field lines that would go like around the bubble? I don't
yeah.
like, I don't know if it does or doesn't. It
Yeah,
makes me
that's
think
true.
that it's possible that the difference, like the presence of a bubble is gas phase, right? Obviously. So does the field just go straight through the gas? Because it's electrical field. It's not. Is it affected or not? Like, I actually don't know.
Yeah.
But it occurs to me that it might, and so I don't know, frankly.
Yeah.
But my only hunch is that I think it's conceivable that the presence of a heterogeneity at like a different phase, like a bubble, could impact the field
Mhm.
between anode and cathode. That's just my hypothesis, just
Yeah.
without any evidence necessarily
Mhm.
per se. That's what I would say. So
Yeah. Yeah. Sorry, Azim. I don't know if we have
yeah,
anything
it's a
extra.
good question though.
That's a very good question.
I like that question.
Yeah. Let's see. So Hasith is next. How do the CV test for rechargeable batteries? How connect working reference and counter electrode? So most of the time, I mean, so if you're doing a CV test on a battery, which I know Neil doesn't usually like people doing this, but if you're gonna do it,
You can.
oh, you can.
It's
Oh,
not-
okay, all right. It's not.
Yeah, I know. It's like I rage against it sometimes. It's true.
But you would want to short the reference and the counter electrode together. So you want to connect those two guys together. You're working electrodes here. So now you have a two electrode setup, and then you would place the I guess the working electrode on the positive terminal, and then the reference counter on the negative terminal of the battery, and then you can perform your cyclic voltametry test. But that's how you would go from the traditional 3 electrode setup for a regular CV experiment to a 2 electrode setup that you can use for a battery. So hopefully that helps you with that.
Yeah. Also, just so you're connecting the reference and the counter together. Just to be clear, working electrode goes on the cathode. Reference and counter go on the anode. That's the. I'm sorry. Did you?
I just said negative and positive terminal.
Yeah. Sorry. I cathode is the positive terminal. So yeah. So the positive cathode is
the working.
Yes.
Okay.
Yeah. So the
Okay,
positive
good.
terminal of the cathode is connected to the working electrode, and the negative or the anode connects to the reference and the counter.
Okay.
That's the correct orientation. And then the CV test is just do a slow scan rate, a really, really slow scan rate. So it's similar to the situation we talked about before. Someone asked about why do you do galvanostatic, and part of the reason is to control the rate, right? Well, when you're doing a CV, you're not, because you're controlling the potential instead. But to prevent really crazy swings in the rate, scan very, very slowly, because the time it takes to get from one voltage to another is the duration of the charge discharge, basically. And so if you scan very fast, it's like charging up extremely quickly and at an uneven rate. So those are both things that will be very undesirable to change to charge up or discharge down like really, really fast, especially in an exploratory fashion, is kind of, it can be dangerous and not necessarily the best idea. In addition to the fact that it's uneven, right? CV necessarily is potentiostatic, and so the rate is uneven. So by scanning very slowly, you at the very least extend the time of your full charge discharge going from one voltage to another, which is a good idea. You limit the amount of rate swings, I guess. So I'm talking about like 0.5 millivolts per second, 1 millivolt per second, or slower, is my recommendation for the CV parameters. So,
All right. Now, Samim is asking, from CV plot, how do we know CO2 reduction is possible or not? This looks like he's repeated this a few times. So the experiment itself, so you rarely can just look at a CV and just know, oh, it's CO2 reduction. But generally speaking, you would want to do like a few CV experiments. I'm on the wrong tab. So generally speaking, let's say you're doing CV voltage current. You may have some kind of catalyst or something. It's not doing anything. You get a nice duck. This is when you have no CO2. But then if you do the same experiment with the same conditions, and all of a sudden you're getting like, oh, I got this huge current here. Maybe it looks something like this. I am terrible at drawing these kinds of voltammograms and stuff like that. And this is with CO2. Then this is evidence, I would say, that you have some CO2 reduction. And actually, maybe what I'll do is, actually, one thing I'm going to do, I'm going to kind of delete this. I'm going to draw this in the, that was actually the Texas convention. I want this to be the IUPAC convention. So this is your, oh God. So this is your CV. Something like this, very bad. No CO2. This is going to be your CV with CO2. So it goes down pretty far. God. I'm just so bad at
drawing is hard today. Just
well, I'm never very good at drawing these things.
They're hard. It's hard to draw. I don't blame you.
Yeah. Let's say maybe you get something like this. So this is like, this one is like with CO2. And then the black one is like without CO2. Now this is very like general, but this also is not exactly, because I've been in situations where, like you see this and it actually wasn't like CO2 reduction because of the nature of the catalyst itself. So you do need to be a little bit careful with this. And let's just see, because if say if you're in aqueous conditions, so this is aqueous, I can't spell. Then when you have CO2, you also inherently lower the pH. So if your reaction, so this could actually be some proton reduction as well, right? You could be reducing protons. So you need to see, like, what is this voltage, right? Is this voltage like, around like, very like negative 1.5 volts or something like that? Like, oh, okay, well, it's really negative, super negative. You're in the potential range where CO2 reduction would occur. Of course, you're also like, this wouldn't happen under aqueous conditions. This would happen more under non-aqueous conditions. But what I'm trying to ultimately get at is like when you look at an LSV, when you have or do not have CO2 reduction, you have to look at cases where you both don't have CO2 and you have CO2, and you try to control for the pH. You need to try to keep the pH the same between the two experiments. And you just have to be very careful. And most importantly, you need to use another technique. You can't always just look at the CO2 reduction in the voltammogram to determine whether or not it's CO2 reduction. You also should try to do an electrolysis experiment and look for CO2 reduced products. So that should hopefully be helpful. And then you can even increase the pressure, right? When you increase the pressure of CO2 in these systems, does that also increase the current if CO2 is a reactant in this reaction? So hopefully that's helpful. I don't know if it's not this, but this is just from looking at a CV plot in general. Okay, Azim has.
I'm not sure if we'll be able
question.
to answer this, but I was just looking
Yeah.
into it, see if I can kind of understand it a little bit.
Mhm.
Yeah, he's saying as we know, electro-wetting, talking about ultra low voltage electro-wetting on conductors effect vanishes as soon as Faradaic process starts. Can you explain why that is, as underlying physics is still CNTD things continued, or that's a different acronym? Controlled nucleation, thermochemical deposition is what I'm getting when I search for that term, controlled nucleation, thermochemical deposition. I don't know if that's precisely what you mean with that. It seems to be. But meaning for this case, the high field concentration inside the electrochemical double layer or its capacitance is responsible for electro-wetting. And everything is the case when we run a pulsed system. So why does it vanish? I don't think I know a lot about electro-wetting in general, actually,
Yeah,
to be honest.
I don't know either.
This isn't the electric field modifies the wetting properties of a surface. So, okay, so basically the electric field changes the like hydrophobicity, not the hydrophobicity, the surface properties, basically the electric field does. I'll continue. Okay, explain why underlying physics is still continued. So okay, so basically the point here is that in a electrochemical system, you have a field that changes the surface like wetting properties, you know, how it reacts with water, basically the contact angle, that kind of thing. And then why does that change when there is a Faradaic process? What the only thing that's coming to my mind, and maybe you can speak to this if you get along the same like track as me, is if there's a difference between homogeneous or heterogeneous electron transfer. If something about that, and again, I'm always screwing up which one's which. Homogeneous would homogeneous transfer would be like tunneling of electrons, right?
Yeah. Heterogeneous is like there's more of like a stronger bonding connection
Right,
between
so-
the electrode and the
right. So
redox
so it'd be
molecule.
that one. So so perhaps the only thing that's coming to my mind, and whether this is the case or not, is that perhaps, Azim, it's something like heterogeneous electron rate transfer is occurring, which is breaking up the surface properties, and maybe that discontinues the electro-wetting process when that's occurring, so that with no Faradaic process, all you have is basically electrical double layer, right? And so there's an electrical field. There's no Faradaic electron transfer. There's charge accumulation from the EDL, but there's but this again, I'm speaking a little bit out of my element because I don't know this like why does that occur, but I'll take that process at face value, that there's an electrical field and this process is occurring where the property is affected. But then you have the electron transfer, and it's a heterogeneous one, which means that there's a like surface bound element to it, right? With heterogeneous electron transfer. Is that right? Something like that?
Yeah. So yeah,
Okay.
Yeah.
So now just make sure
depends what the metal is.
I always screw that up.
Yeah.
So I always have to ask you to remind me and make sure I'm saying
Mhm.
it right. So that's all that I can think that would make some sense as far as like, why is the surface property changing when you have a Faradaic process? Well, if the Faradaic process is a heterogeneous rate transfer, perhaps the adsorption or proximity of species on the surface is causing a change in the surface property during that time that you have a Faradaic charge transfer if it's a heterogeneous. Because a homogeneous one is like electron tunneling, and there's that wouldn't perhaps change the surface condition. Maybe it would, but it's the tunneling process means that the effectively species doesn't have to be directly absorbed, like physically touching the surface, that the electron sort of tunnels through the EDL, something like that. So perhaps it's heterogeneous rate transfer. That's my guess. I don't know if that's correct, but that's, I would say, a relatively educated guess. I don't know if I have any more possibility of answering than that. That would be my stab at it, I guess. I don't know if you have anything else to add, but electro-wetting is not something I'm familiar with either.
Yeah, I don't know very much about it at all.
It kind of makes sense to me because it's an electron surface, electrode surface change, right? Due to an electric field, I guess, or for whatever other reason. So if something in the electrochemistry is causing that to discontinue or vanish, something has to be interacting with the surface in some way, and a heterogeneous like a heterogeneous electron transfer, right, is a surface, a process that like directly affects the surface. It makes sense in my mind at a quick glance. So I don't know. That's my proposed answer. And someone much smarter than me probably explain how that's wrong. But that's my guess.
Yeah, I would need to learn. I just need to know more about like electro-wetting. I don't know. I really don't know anything about it.
Yeah.
So.
Well, maybe take that answer and ask somebody smarter than us, Azim, if they
I
can
have to look
confirm
into
that
it.
makes sense. That's the best I can do for you. That I would say is at least reasonable for my quick estimate there. But sorry we couldn't give you a definitive answer. It's not perhaps within our knowledge base, definitively, I suppose. So we'll move on here. We have a couple minutes left. We'll try to get to the last few questions, I guess. Divya says, in the Randles-Sevcik equation, how do I find the electrochemically active surface area? I don't know that you can directly.
Well, I think it's just like, how do you find the electrochemically active surface area so that you can use the Randles-Sevcik equation, correct?
I'm just trying to think, like,
because the area is in the equation.
Yeah.
But it's like, but I'm trying to use it to solve something else, so I need to put the area in.
I'm just thinking, like, if you plot peak current versus the square root of the scan rate, and you know the diffusion coefficient and the concentration, you could, in theory, extract the area. The question is that the ECSA, or is that just the geometric area?
I
guess it's
in that case it's the I guess in that case it's the ECSA,
I suppose. But you're making an assumption about what the other constants are, so there's a possibility there. I guess my point is, you could, in theory, take the Randles-Sevcik equation here. So just look at the terms in this, right? We have looks like V, but nu or epsilon, whatever the right variable is, to the 1/2. That's the scan rate, right? And IP, which is the peak current. So you can measure peak current at different scan rates, take the square root of the scan rates, and plot peak current versus the square root of the scan rate. And then you have 2.69 times 10 to the 5th, whatever. You have n number of electrons to the 3/2 power. Well, if you know what Faradaic reaction you're studying, you know n. If you know the concentration, C, and you assume usually the Randles-Sevcik equation is used to calculate the diffusion coefficient, to be honest. But let's say you know the diffusion coefficient, or you're assuming it. Then you could instead fit a straight line for peak current versus the square root of scan rates and extract the area that way. it's part of the slope, right? It's just based on this equation. If it's like followed, if your data follows this trend, ideally, you can extract A from that. So that's I guess that's how you do
That's
it.
how
I
you
mean,
do it.
yeah. I guess that's the answer. I don't know if
That's
there's
the,
anything more
I
to
think that's the
say.
answer. Yeah, I think you said it.
Yeah. So, but I think that the only thing I'd say is that could give you some error. I think it's possible that could give you some error, only because I think you're making some assumptions. You're making some assumptions about the diffusion. Maybe, is that accurate or not? I guess. And
Well, it's like if you have a big molecule, for example.
mhm.
So like the reason why the electrochemically active surface area on platinum works so well is because it's hydrogen,
Mhm.
and hydrogen is the smallest atom. So there's no doubt that it's going to be able to find every single active surface site on the platinum when you're able to determine what the area is. But if you have a bigger redox molecule, and you know it may be the case that because the redox molecule is very big, it goes over more than just one site. It sticks to one site, but ends up blocking like several others. So the active surface area, sort of say, is an it's an underestimation because
Mhm.
if the molecule's too big, it gets blocked. So that's kind of the trade-off between them. But if you're just trying to figure out, I mean, it's also not a bad estimate. There's kind of an assumption there, but that's kind of the questionability. I mean, a lot of people actually just use the geometric area when they try to calculate diffusion coefficients for some of these things. So,
Mhm.
um, especially when they're using the Randles-Sevcik equation.
Yeah. I think this last part here, Onion Way has asked, am I able to do a video showing how to calculate heterogeneous rate constant using RDE? I have done that actually. In fact, I've given a webinar on RDE,
Mhm.
Levitch analyses. I think twice I've done this webinar series, 2 or 3 times
Yeah.
I've done it. I'm going to link to those videos if I can find them for you. And
Or you can also find them on our website as well.
yes,
We have
yeah,
it's
that's
kind of
probably
like
better, right?
organized a little bit differently, but from our webinars playlist,
Yeah, do you have the link? You can put the link there.
I'll put the
Okay.
link in here. So it's our website. You go to webinars, and then you can go look at all the webinars. Most of them are on EIS and how potentiostat works. But there's some on RRDE. So the one that's on RRDE, theory, real experiments, and then data analysis, that will go over how to calculate, like the steps you would take to
Yes.
calculate the heterogeneous rate constant using
So
RDE.
there's 2 of them: RDE, data analysis, Levitch, Tafel, and collection efficiency. There's 2 of them. The first one I show the theory of it, and the second one I actually do the calculation live with Excel in that webinar. And I will be repeating that webinar at some point. I always like to try to repeat my webinars once a year or so. So I've done that. Check out our webinar on our YouTube channel. It is for members, so you have to be a YouTube member to get that video. But if you want to join for any amount of time, you can watch that webinar, and I talk about how to calculate the heterogeneous rate constant. Okay, so are we gonna? What do you think we'll call it here?
Yeah, we'll call it here. It's been
Okay.
great. Sorry we weren't able to get to all the questions,
Yeah, I
but
see. There's one other question about just reproducible data. I mean, welcome to the club. It's hard to get reproducible data.
yeah,
Definitely a thing. I don't have a lot. We could probably talk forever, actually, to be honest, about strategies there, but we are a bit out on time here. We do this for about 2 hours. We start at 1 p.m. Eastern time on Fridays. And so if you have questions you want to get to, we encourage you to try to get in the beginning of the time. We do try to get to everything, and it's not always possible in the time, I suppose, but we appreciate everybody. And thank you again for anybody that was able to meet up with in the Montreal for the Electrochemical Society meeting. It was good to meet a few people. I took a couple of pictures with some people, I think, and it's always nice to meet people that appreciate our YouTube efforts and stuff, and 100 episodes, of course, which was last week. But anyway, thank you everybody again, and I hope everybody has a great weekend, great week. If you're in the United States, it's a long weekend for some of us, Memorial Day. So have a good long weekend. Hopefully you have time off. If you're in graduate school, I doubt you have time off, but that's just how it goes. And we'll see you next week. So take care, everybody.
Bye.